and we are going to talk about a predictor today mostly, but I would like to remind you as generally what we are providing in engineering community that Total Materia have over 20 years of experience, and every month we are updating Total Materia. We are providing you different solutions, and we are also upgrading these solutions as well. Today with me, Mr. Gianni Lelie. He's a mechanical engineer, and he is specialized about application and predictor development team as well, and he's helping us a lot. He will be talk about the predictor in detail, and he will show you actually how we can get advantage in predictor and how we can use it. So in briefly, Total Materia is providing Horizon to you with a whole material information and data set. So many of you know Total Materia very well. You can get a lot of information in once. You can compare materials, over 600,000 of materials, over 20 millions of properties. So it's including fatigue data to stress strain curves. And this is basically in generally all you need about the materials. Anytime you want, you can test it again, you can discuss about your license, and in the same time that we are providing different solutions, that which one of those is integrator private enterprise solution for your materials intellectual property, so you can create your own internal database. As you can see here, your materials or Total Materia to reach in the same time. You can create your own database, and anytime you want to see more, you can contact us and we can arrange some demo or details. One of our solutions is also Greenline. Greenline is responsible for material selection, sustainability, and compliance issues. It's including a lot of different actually functionality, I can say, MOM assessment to LCA, and it's so detailed. So today we are going to talk about more in details. And predictor is material property modeling and prediction using machine learning, what I call is a testing simulator, isn't it, a little bit, Jenny? As Total Materia AG, we have an algorithm that we created and provided since 2007. Actually, it's a smart comp, can define a material. We had this base, we had this knowledge, and now it's beyond that. Predictor can provide you so much more, and Mr. Gianni will tell you about the details and how actually you can use in predictor. And can you please, Gianni, briefly tell us about yourself? Now you can share your screen.
So just to present myself shortly, I'm a mechanical engineer for 15 years. I worked in different sectors from minting to pharmaceutical, and I also was working for Airbus, material testing, and for GDF, Suez in France, for creating a predictive model for corrosion of gas lines. So maybe I should start with shortly with predictor. So I opened two windows so that I can show you in parallel. And there are several use cases we are addressing with predictors. So as Zaim introduced, we are filling the gaps, but also helping to reduce the testing campaign costs and waste of time doing them. So if I may show you, for instance, here, a very common titanium alloy. But when you go see what's available in the literature, you will see that there are many data available, but physical properties are pretty much absent from this reference, at least. So with Total Materia and this little star here, we are already filling part of the gap through cross-references. So what I can do, I can go to another reference, which is 100% equivalent in composition. And for example, search here for the coefficient of thermal expansion. I will find some data, but it's rather limited. You see, I only have it at 20 degrees. If I want a temperature dependency, for example, it will be hard to fill the gap with this. So that's where Predictor jumps in, and where I can very straightforward go enter my designation. So I search for it in the same manner as on Total Materia. And here I will then find my reference. I'm able to select in which standard do I want my reference. So let's just, you see the chemical composition slightly changes. Let's say I'm using this standard, and I will go forward. So this step can be improved, but it for now gives you all the possibilities to make the best predictions by offering you 3 ways of predicting. First, synthetic value. So it gives you a range independent from the condition of the material. And then if you want more precise values, really dependent on the condition, so heat treatment, form of delivery, you would go for one of these 2 models. Deep learning is the most common artificial intelligence when you hear someone speaking about it. It works very well when the data is abundant. When you have a lot of data to train your algorithms, this is the most performant one. It really creates all the connections between the parameters, finds the covariances, and really provides you the best result. But as you may know, some data points are more scarce than others. So in order to also provide these, we also implemented GRNN, so General Regression Neural Network, which works much better when the data is limited in quantity. It provides a much better approximation in those cases. But for our case, I would recommend to go always for deep learning, because we implemented a feature that tells you in which circumstances you should use another one. So let's go forward here with deep learning. And we looked at coefficient of thermal expansion. Let's give a closer look. So I will predict this property maybe between 0 and let's say 800 degrees. And I would like a data point every 10 degrees. And it is as simple as this. You simply enter your condition in which you want the property, and we provide you with the prediction. So here you see the results in the form of a graph, or the values that you asked for every 10 degrees, as you can see. And down here, we provide you with the model testing. So a little bit more background on this. We trained our algorithms with the data available in Total Materia. So as you may know, it's the largest database of material properties in the world. But to make sure that the data we are generating with those predictions is accurate, we decided to keep 20% of the data points aside. So not to give it to the algorithm ever for training. And then we use those 20% to ask questions. In this case, what is the coefficient of thermal expansion of this specific designation? Then the prediction comes to us and we can compare one-to-one. And those testing performances that you get down here are the synthetic statistics of this comparison. So what does it tell us? So here you have the general statistics. So mean average percentage error, 2%. What it means in terms of coefficient of thermal expansion. So mean average error of 0.181, 10 to the power of -6. You have root mean square, which is a bit more sensitive to small variations than the two others. And we also provide you R and R squared in case you prefer to rely on these parameters. One which is really easy and straightforward to understand is this prediction within relative error. So in the questions we asked, we had 94% of the answers that were within ±5% of the real value. If I increase in a range of ±10%, we had almost 100% of the predictions. And this little statistic frame down here is provided so that you can easily judge, quickly judge if the predicted values here are reliable or not. So once you generated this prediction, you might want to take it away, of course. And for this, we provide you two options. So add to a report and make a PDF, sort of limited for our use case. But we also allow you to take it out in Excel format, where it is, this is for later, where it is here, very straightforward. The condition that you predicted, that you asked to predict, the values that you wanted, and down here, the model performances. So to always keep it with the data and justify it then in your reports. So that's one of the use cases. Pretty much straightforward. Of course, I didn't mention that you can save your prediction on the platform and then share it later with your colleagues. So if I go a bit deeper, so you've seen here, I entered one designation, I got the reply. Let me just give a look to another one. So here, this aluminium alloy, which has been defined kind of recently, and where the data is very scarce. So let's go for AA. What do we have? We have the density, like every aluminium, and the composition. But what are its mechanical properties? What can I expect from this alloy? So if I search for it in predictor, so I can select it, go to the next step. This time I will maybe search for mechanical property, tensile strength, and here I then can choose the condition of my material. So for the first one, I will go for a very common T6, maybe for 20 millimeter bars in longitudinal direction between 0 and 300 degrees, and a data point every 20. And very quickly, I get an evaluation of the tensile strength of this material. So again, down here, the performances of this model. So this model means 4 aluminiums in this condition. So here I got a prediction, but let's see how it performs in different heat treatments. So I will add this diagram to a comparison. And I will simply go one step back and say, oh, how does it behave if I make a T8 on it? So I get another prediction and add it to my comparison. How does it react with maybe a T3? I'll just do a few for us to have data for comparison. And maybe how does it behave with a simple heat hardening? And here with this tool integrated in Total Materia, I can very quickly see the differences in the heat treatments and their effects on this material. So here we see that the number one, the blue one, is kind of similar at room temperature, but as we move on with higher temperatures, between 150 and 250 degrees, it's much weaker than the others. And do I have a real benefit of going from a more common T6 to a T8? Well, if I zoom in here, well, around 200 degrees, around 200 degrees, I don't have a real improvement. Maybe of 20 megapascal, 10, 20. So is it worth it? I let you decide. So that's another possibility of predictor. You see, at once I predicted different heat treatments, but also I filled the gap in a material which is not documented in any literature. So I spare you the testing, and with predictor, I also help you choose the best heat treatment for your application. So, and another use case, yet another one. So you've seen here I was in material and I was typing in designations. So this is very common way of approaching materials. But there is another way, is making your own composition. So here I will maybe this time switch to a ferrous alloy. I prepared here, let me close this. I prepared here a very basic stainless steel. So 19% chromium, 10% nickel, 0.04 carbon, and manganese and silicium. So I will import this into predictor. Like for SmartComb, it fills in cells, and then I can go for a prediction. Let's say this time for this stainless steel, I'm interested in the yield strength of 5mm plates that were annealed at 1050 degrees. Let's predict between 0 and 600 degrees with steps of 10, for instance. So here I get a prediction. Again, with the model performances, as we see here, it is very, very performant, less than 1% mean absolute error, and almost 100% of the prediction between plus minus 5%. So using this, I will again use Total Materia to compare. So diagram comparison, and I step back to the first. Here I had a little problem with my connection this morning, so it's not keeping the data, but that's related to my browser more than the platform. So just let me go forward. I reconfigure exactly the same condition. I set plates, right? 5mm. I think I nailed it at 1050. My use case was between 0 and 600 degrees and every 10 degrees. So again, I generated the same, I added, all right, let's step back. And what if I reduce my carbon? So you ask anyone, they will tell you, oh, well, the material will be weaker. All right, let's give it a look, we'll compare. And I will just add a bit more carbon this time to see the other side. So in my yield strength, here I have my different compositions, a reminder of the condition of the material. And I can easily see that with 0.06% carbon, I'm much stronger than the standard one at 0.04, or the lighter one, I mean cheaper one at 0.03% down here. So that's one use case, but we could also consider, oh, okay, but what if my supplier is cheaping out? So I will just regenerate the common one. You see how quick it is to make a prediction. It's almost instantaneous. And what if I'm cheaping out a bit? What if for my corrosion resistance, I could live with 13% and here 8%? Would I lose much in resistance? Or what if I go down to maybe 12? Oh, that's outside of our model. You see, you get a little warning that we will be extrapolating. So you see, everything is controlled through the steps. You are always warned if you're doing something out of the ordinary. And we clearly state you that those points are extrapolations. So at no point you are surprised by the data you get, and you can always evaluate if you can use it or not. But let's see for the comparison. So again, I will give a look at my tensile. And here I can then easily see the effect of my different compositions. So we see that when I have a bit more nickel, I'm a bit stronger. I mean, nickel and chromium. And when I start to cheap out, sorry, my mouse is misclicking. But when I start to cheap out, I see that I have a gap here that appears. But reducing 1% chromium, if I don't need it for my corrosion resistance, it should not make a big difference. All right. Last point that we could also consider is here, defining your own BA66. So here, for instance, I can predict the same way I did it for metals, the properties for a polyamide. For example, I could add some glass fiber in it, around 18%, let's say, maybe some flame retardants, and I have no idea of the density that I'm currently having. It's predicted, should be around this value. And I can then go for a prediction, for example, of the impact strength with a water content, for example, of 1.1%. And I would like to have the Sharpie unnotched, for example, at 50 degrees, or let's say 55. And here you get an estimation. And again, you see, you're always told the applicability of your value. So in this case, you see that the mean average is way bigger, that our predictions are way larger, and this is the case for all the polymers, because this only reflects the data available in the world. Because currently, for polymers, the data is held by the producers, which often only provide the value that they want to market. And all the other values in the data sheets are more or less typical. So in those conditions, it's hard to make good predictions. But we nevertheless wanted to offer this as a demonstrator of the capabilities. If you have your own data, we can help you also build your own predictions. So what's currently available in Predictor? It's very easy to give a look. So we created models for all these material groups. So in ferrous alloys, we can predict stainless steels, highly alloyed, low alloyed, with high or low carbon, and in non-ferrous, commonly asked are aluminium, copper, nickels, and titaniums. So all these material groups, so I've demonstrated a few, are available for predictions. So either in with the material designation or the composition that you can compose yourself. So maybe you have some questions and Saim can.
Exactly, one of the most common questions that we can start.
Well, it's actually about the prediction of strain rate, and can we able to extract strain rate data with this method? Or are we planning, as you know, as we know, and would like you to know, Predictor is upgrading every month. We are adding some new material groups, and some new functionalities, and maybe also you can would like to talk about some details about because you're the application manager.
Yes, of course. So currently we are, as Saim said, updating every month. So for example, this month we added cobalt and nickel alloys, as well as complemented some steel models. And we are looking forward to add for third quarter or fourth quarter this year some predictions on fatigue or stress strain. So that would fall within the strain rate dependency. But for now, I cannot promise you anything, because apart from polymers, we are putting our standards very high. We are not releasing a single model that is about above 15% accuracy. And 15, I'm taking the real maximum. So if we are unable to create a model which predicts accurately, we are not releasing it, and we keep working on it. So for the moment, we had very good results in fatigue. That encourages us to build better models. But a big part of the work is formatting the data and curing the data. So making sure that every data point that is given to the algorithm to be trained is in a correct format, in a unified unit system, and that the source is reliable. So currently our teams are double, triple checking all of this before giving it to the algorithm. So big part, I think you understood it, is the data that comes in. Because Total Materia already has more than 200,000 data points in nonlinear, we are pretty much confident that we will make accurate predictions. But it's a lot of work, and anyone can build or take an algorithm of artificial intelligence, but the result really depends on the data that comes in. If you put crap into the algorithm, it will always give you an answer, but this answer will be crap.
Well, that's the main advantages on Total Materia solutions. Back in the days, 2018, I remember we were also presenting, this is not estimated values that in Horizon, this is not approximate values that we can provide. If it's correct value, then yes, we can add it into Total Materia, and now it's Horizon. And the same approach in here in Predictor. Obviously, beginning of this week, and previous week, I had some in private predictor meetings with some engineering groups and some companies, and they had like, okay, let's prepare this predictions with our actual tests, they said, and we literally choose the material that they are testing, and at the end, they have the real actual test results, and we just compared with the predictor, and they said, okay, we basically and obviously lost some time and money with that, and predictors predictions and the results that predictor is providing here is actually almost the same as we did this test to this material. So being so precise and providing you really detailed and precise material data are the most important part for us, and I'm sure it's testing and it's going to be online with the perfect way about predictor. So there is another question also about the predictions. Maybe you would like to answer. Is the database or solution provides only from provider values, like it's on its own, or do you use academic publications as well? That question.
So to train the algorithms, we use the data available in Total Materia, and in Total Materia you find standard provided values, values also from industry handbooks, but as well we rely on academic publications. But all of this is always controlled by the copyrights. So sometimes we get in touch with the authors to get the data, and some other times when they make it freely available with under Creative Commons, we can directly enter it. So it's a big part of our work also to make sure that the data we are providing is accurate and that we have the right to use it. But yeah, we include academic publications also. For a big part of the nonlinear data, because as you may know, those data points are often from test campaigns that were made in universities, so it's rarely provided by standards.
Yeah, that's the main problem usually, or sometimes you're working with a special material and you would like to have the properties of the material, cannot find it through standards, or any producers are not providing any data. So we are not putting estimated data here. We are not providing you some generated data, but needs to be precise.
For instance, here you have a few publications, for example, from these researchers from Japan, or others that you can see here in the list. So some are very old, but still still industry standard nowadays. And you can see that in the list we have either handbooks or we also have publications. That's often the case in nonlinear data. So if I go to fatigue, You will see here, for example, an aluminium handbook, some publication from Alcoa, as well as more research-focused data with, for example, Japanese Society of Mechanical Engineering, or here material data from Elsevier, etc.
So, is there any other questions that you would like to know? As you know, you can always reach me. I will share with you the recordings of the webinar. You will recheck. If you would like to test predictor, let's have another detailed meeting. Let's discuss. Let's try to answer your questions. Whatever comes into your mind, you can feel free to share with me. And Johnny is here, very experienced application manager of Total Materia. And yes, that's the main point. I can say that maybe it's very interesting because I was looking forward to have Predictor online for a long time, and it took too long for us to test because everyone here wants to be sure, 100% sure that we are providing something very accurate. That's our always target.
So if I can just jump in and complete Zaim's proposal for testing, what I would really suggest you, because we, unlike the Horizon database, where you have unlimited testing for 2 weeks, Predictor is limited to 5 predictions within a test account. So I would really advise you get use cases where you can maybe compare the real data that you have with our predictions to see how performant our models are. So really get your test cases correct, or test cases set before testing, but we can also help you in setting up such tests. No worries.
We have another question. Failure
strain rate. Again, for strain rate dependent data, that's coming later. I'm afraid we still have.
Can you give us a date, something approximate data? We're not providing or sharing any approximate data, but maybe you can share some approximate dates.
So yes, as you know, I'm not keen of giving dates. I'm not keen on doing this, but we expect it by the end of the year. We expect to have strain rate dependent data by the end of the year.
Okay, that's a good news. That's a good news. Oh, you're welcome, Mr. Professor Daria Dishpinar. He's with us today. And please, I would love you to try this, Daria Dishpinar. Of course, you may test Predictor, yes. You can contact us anytime you want, and you can send questions, anything comes into your mind. You can reach me by my mobile or email, the way you would like to. If you have any questions, Mr. Genevieve Lullier here with us today to answer every questions about Predictor and detailed information that if you want anything to ask. What I would like to ask, it's very important in CAE software that you're using a lot and different kind of simulations, and you actually created some simulations. Can you talk about it?
Yeah, I created a simulation for well, how to make it clear. We have 30,000 kilometers of high pressure gas lines in France between the different production sites, between the entry points of the country up to the different cities. And those lines are obviously buried on the ground between 2 and 5 meters deep. And they were put there between 30 and 40 years ago. So now they start corroding, and we cannot dig out 30,000 kilometers to check if there is a risk of leakage. So the French gas company developed a tool that with an electromagnet that travels through the tube will measure the remaining thickness. But because of GSM networks, because of high voltage lines, the accuracy of the measurement of the remaining thickness is plus minus 30%. So what I did is I developed a predictive model that takes those measurements, applies probabilistic models built on those statistics to determine which sections will have to be taken out of ground to be checked more thoroughly and to be replaced. And this proved to be accurate over 20 years. So over the 20 next years, those predictions are running and predicting that in 2 years they will have to inspect that kilometer 500 from this point and so on, and to dig it out. And from the feedbacks I got from the users, so I did this almost 10 years ago, I'm still in contact with them. It's pretty much still accurate. They find the corrosion points and the evolutions that we predicted. So it spares them millions like this. And this would not have been possible without exact data on the materials that were used. So without exact data, we couldn't have done predictions, for example, on corrosion progression or on the resistance of material. So like for every calculation, if you take approximative data in, you get approximative data out.
Yeah.
And if you want to optimize your costs, if you want to optimize the performances of something, well, you need optimized data input. Doesn't matter how precise your calculation method is, if you don't have precise data in, you don't get precise data out.
It will lead you to the wrong estimations and wrong results, just like we had faced with some of our defense industry companies. They had some simulations. They are sure about the results. At the end, they are making this prototype, and you see like, okay, why it's behaving in this way? Let's say go back and recalculate your estimations and simulations. It's not really accurate, obviously. Then your prototype behaves completely different. So these are very, very important informations. Is there any other questions? Thank you very much, everyone. And I will share with you the recordings, and you can contact my email anytime if you have any questions. Johnny always around here, and I can ask some help from him. So thank you very much. See you next time, next webinar.
Thank you. All right.